Good morning po. My name is Joyce and Francisco and my report is all about plate girders. Continuation po ito ng report ni Miss Christine Valyagar. Start po tayo. Stiffener moment of inertia. In addition to satisfying the geometric requirements, the designer must also ensure that the moment of inertia of a stiffener is greater than a specified limit. The moment of inertia for a stiffener on one side of the web only is taken about the face which is in contact with the web. If stiffeners are present on both sides of the web, then the moment of inertia is taken about the center line of the web plate, according to AASHTO 10.48.5.3 and LRFT 6.10.11.1.3. Once the moment of inertia of a given stiffener, I, is known, it must be checked to see that I is greater than d sub o multiplied by t cubed sub w multiplied by the required ratio of rigidity, where d sub o is the transverse spacing between stiffeners unit in inch, t sub w is the thickness of web in inch, J is required ratio of rigidity of one stiffener to the web. AASHTO defined the required ratio of rigidity for a single stiffener to that of the web plate as ratio of rigidity is equal to 2.5 multiplied by d sub d all over d sub o squared minus 2 but not less than 0.5, where d is equal to unsupported depth of web plate between flange components for transversely stiffened girders, or maximum sub-panel depth for longitudinally stiffened girders. Generally speaking, most stiffeners were consistently meet at the moment of inertia requirement. As in the case with any design requirement, however, a consistency in satisfying design criteria does not imply that the right to forego the process of checking. Next is welding transverse intermediate stiffeners. With respect to the connection of the stiffener plate to the plate girder, an intermediate stiffener is not required to be in bearing with the tension flange of the plate girder unless it is used to connect diaphragms. One of the reasons for this is that when a stiffener is welded to the tension flange of a plate girder, the tension flange will be subject to fatigue. Therefore, it is permissible to stop the stiffener short of the tension flange plate. The distance between the end of the stiffener weld and the fillet weld at the closest edge of the web flange interface weld should be such that 4 sub tw is less than or equal to d sub weld less than or equal to 6 t sub w, where t sub w is thickness of the web plate. Number 6. Transverse intermediate stiffer economy. From an economy standpoint, transverse stiffeners should be placed on one side of the plate girder web only, whenever possible. Exceptions to this general rule would be at diaphragm connections for interior stringers or the other points intended to support concentrated loads. Number 7. Bearing stiffeners. In section 3.10.9, we briefly discussed the use of bearing stiffeners in conjunction with rolled beams. An illustration of a bearing stiffener was also presented in figure 3.38. Welded plate girders are required to have bearing stiffeners at the end bearing locations and intermediate bearings of longitudinally continuous structures. At these locations, the bearing stiffener is designed to resist the total end reactions. AASHTO recommends that a pair of stiffeners be used. In example, a stiffener plate on either side of the web. It is even possible that when a girder is excessively deep, the web is designed to be equipped with 2 pairs of plates. If this is the case, the plates should be offset sufficiently to permit proper welding. Ito po yung figure 3.41, connection of an intermediate stiffener to plate girder. When a stiffener is attached to only one side of the web plate, a AASHTO requires that the stiffener must be in bearing against, but need not be attached to, the compression flange in order to be effective, according to a AASHTO 10.48.5.3. An exception to this rule would be if the stiffener plate were also acting as a connection plate for a secondary member. See Section 3.11.2, Part 5, Single and Dual Stiffeners. In Figure 3.41, stiffeners are provided on both sides of the web plate and are connected to the compression flange with a fillet weld to both sides of the plate. The main functions of the stiffeners are to resist compression forces which are transmitted directly from the web and stiffen the web during buckling. As mentioned in the sidebar accompanying Figure 3.38, bearing stiffeners are designed as columns, resisting the end reaction of the span. The width of each projecting bearing stiffener should satisfy B sub F less than or equal to 0.48 T sub P multiplied by the square root of E all over Fy, where B sub F is width of stiffener in inch, Fy is the yield strength of steel used for stiffener in KSI, and T sub P is equal to thickness of projecting stiffener element in inch. Bearing stiffener should also be designed to resist the factored bearing forces. The factored bearing resistance can be calculated according to AASHTO LRFT 6.10.11.2.2 or R sub B sub R is equal to the resistance factor of bearing sub B, the resistance factor of bearing multiplied by R sub SB sub N, where R sub SB sub R are factored bearing resistance. Resistance factor of bearing is equal to 1.0 according to AASHTO LRFD 6.5.42. R sub B sub N is equal to 1.4. A sub Pn Fy or nominal bearing resistance, and A sub Pn is equal is area of bearing stiffeners directly bearing against webs. The area clipped to clear the web to flange filled web, and the area beyond the edge of flange, if any, should not be included in calculating the bearing resistance. In detailing the interface of the stiffener and flanges, the designer has two options. Either the stiffener can be 1. Milled to bear against the flange through which they receive the total end reaction, and 2. Connected to the flange using full penetration groove welds. Number 8. Longitudinal stiffeners. A longitudinal stiffener, like transverse intermediate stiffeners, is welded to the web plate of a plate girder. The longitudinal stiffener, as its name would imply, runs along the length of the stringer. Longitudinal stiffeners are typically provided on only one side of the web. In addition to allowing for an overall reduction in web thickness, a longitudinal stiffener also serves to 1. Increase the shear and bending strength of the girder, increase lateral stiffness. Longitudinal stiffener moment of inertia. Like an intermediate transverse stiffener, the designer must ensure that the moment of inertia of a longitudinal stiffener is greater than a specified limit. Once the moment of inertia for a given longitudinal stiffener is known, it must be checked to ensure that it is greater than a prescribed minimum according to AASHTO 10.48.6.3, or I is greater than or equal to D multiplied by T cube sub W multiplied by 2.4 D sub O squared all over D squared minus 0.13, where I is the minimum required moment of inertia in inch to fourth, D is the unsupported distance between flange plates in inch. T, T, T sub W, thickness of web in inch, and D sub O is the spacing between transverse stiffeners in inch. This is the figure 3.42. Typical plate girder detail adapted from standard plans for highway bridge. Volume 2 structure steel superstructures. FHWA reference 3.9. A longitudinal stiffener center line is located a distance of d all over 5 from the inside surface of the compression flange according to AASHTO 10.48.6.1. In this particular detail, the longitudinal stiffeners are to be stopped 2.5 inch or 63.5 millimeters short from the point where they intersect connection plates and web splice plates. Longitudinal stiffeners are not required to be continuous and may be cut at intersections with transverse intermediate stiffeners. In AASHTO LRFD 6.10.11.3, the designer should determine the stiffener location so that both service limit state and strength limit state requirements are satisfied. This moment of inertia is taken about the edge in contact between the longitudinal stiffener and the web plate. The radius of gyration of the stiffener should also satisfy R is greater than or equal to D sub O multiplied by the square root of Fy all over 23,000. AASHTO standard. Equation 3.122a. And R is greater than or equal to 0.253 D sub O multiplied by the square root of Fy all over E. AASHTO LRFD. In calculating the radius of gyration, a centrally located web strip equal to 18t sub W inch width should be considered as a part of the longitudinal stiffener. For hybrid girders, some modification to equation 3.122b is required by the AASHTO LRFD 6.10.11.3.3. Next, geometric requirements. While AASHTO does not specify a minimum required area for longitudinal stiffeners, a minimum thickness is defined. The width of longitudinal stiffeners should not be wider than B sub L or less than or equal to 0.48 T sub S multiplied by the square root of E all over Fy, where B sub L is equal to width of stiffener and T sub S is the thickness of the stiffener. This requirement is intended to prevent local buckling of the longitudinal stiffener. Longitudinal stiffener economy. We mentioned earlier that longitudinal stiffeners are typically placed on one side of the web plate only. A way of improving the overall economy of the fabricated plate girder is to place the longitudinal stiffener on the side opposite from the one containing the transverse stiffeners. Such an approach will minimize the number of times a longitudinal stiffener intersects with the transverse stiffener and thereby decrease fabrication costs. Next is the miscellaneous economy issues. The Bethlehem steel studies bore out some other results with regard to plate girder economy, which are worth mentioning here. The reduction of the number of the girders throughout the cross-section of the superstructure can also play a role in reducing the overall cost of the structure. Although reducing the number of girders can usually reduce the cost, we should not design a bridge with fewer than 4 girders. Otherwise, it will be very difficult in the future to replace the deck in stages or to maintain traffic in half of the deck while replacing the other half. Designers should always keep the future maintenance and rehabilitation in mind when designing new bridges. Lateral bracing for plate girders. Lateral bracing was discussed earlier in the section on secondary members, section 3.1.4, part 2. In summary, lateral bracing in a system of cross frames located in the horizontal plane and installed at the beam's flange in order to resist lateral deformation. Lateral deformation is induced by loads which act normal to the center line of primary members. Wind loads are the major contributing loading condition which determine whether or not lateral bracing will be required. Since plate girders can become exceedingly deep in comparison to their rolled beam casings, the need for lateral bracing is of greater concern. The following is discussion of the general parameters which define the specification of lateral bracing for plate girders. 1. Where bracing is located. The need for lateral bracing should be investigated not only for the final stage but also for construction stages. Lateral bracing at final stage is not required at a flange which is attached to a concrete deck or a deck of similar rigidity. Put simply, lateral bracing for highway bridges is typically located at the bottom flange only. 2. Bracing as function of span length. Previous editions of the AASHTO specifications required lateral bracing for all spans greater than 125 feet or 38.1 meter. More recent editions, however, do not rely on span length as the steadfast rule for incorporating lateral bracing. Rather, the stress induced by wind loads is used to determine the need for a bracing system at the bottom flange. Placement and types of lateral bracing. Number 3. Should lateral bracing be required, it is placed in the exterior base. In example, between the fascia stringer and first interior stringer. Between the secondary members, the bracing is to be placed in the horizontal plane of the flange being braced. So, ito po yung figure 3.43. Plain view of typical lateral bracing layout. Refer also to figure 3.5 for a view in cross-section. Number 4. Eliminating lateral bracing. Some transportation departments wish to eliminate the use of lateral bracing. In certain instances, there may be no way to avoid the incorporation of some form of lateral bracing system. There are, however, some design approaches which may eliminate the need for lateral bracing. Economy of lateral bracing. Number 5. A reduced cross-frame spacing means more cross-frames would be associated increase in cost as a result of more materials and additional fabrication. These factors, combined with the benefits lateral bracing has in the field or with regard to erection, should play in the final decision as to implement lateral bracing or not. 3.11.4 Cross frames for plate girders. As discussed in part 1 of section 3.1.4, a cross frame is typically composed of steel angles in cross or X or V configurations. The primary functions of a cross frames are 1. Transforming lateral force from bottom flange to top flange and concrete deck. 2. Providing stability for compression flanges. And 3. Distributing vertical loads among girders. The spacing of the cross frame should be chosen to balance the cost of the cross bracing and the cost of increasing the bottom flange size due to bending from the lateral wind. The cross frames should be designed to resist wind load acting on the bottom half of the exterior girder. The force should be transmitted to the top flange that is connected to the concrete deck. Reference, Bridge Engineering Macro Hill 2006. And this will end my report. Thank you.